Welcome to Practical Deep Learning for Coders, lesson 23. Today we are going to be joined by...
We're on chapter 8. I don't know what this whole lesson 23 is. We're chapter...
Oh, yeah, that might have been confusing.
No, episode 23.
Right, that's what I meant.
Yeah. Let's not confuse everyone.
All right,
we're not that far along.
Clarifying.
I appreciate the ambition, though. All right, so yeah, let's
quick recap.
Do it. Recap. Last time.
Sure.
Test time augmentation.
We did something there, right?
Test time augmentation and
let me see. Collab 7. So we are progressive sizing.
Progressive, that's the word.
Augmentation. And we got a teacher here tonight. Welcome. Hello, jonovision. Is that working? Connecting to audio.
Connecting to audio.
Wow. So this is really happening.
This is really happening.
Making up on his promise. That's nice.
Yeah. All right. So you want to load up chapter 8?
It's already. I'm so prepared. You have no idea.
Wow.
Look at this. Shabam.
Shabam.
It's here. I already installed. But so maybe jonovision's gonna share the screen or something. We'll see. I'm not gonna type. I don't know. Can you hear us?
Can you hear me? I can hear you.
Yes.
Hey.
Nice.
Well, welcome.
To figure out. I don't know what my sound is going in through right now. Is the sound crappy or?
It's I mean, we could hear you. It's a little muffled, but or maybe it sounds like laptop microphone.
Yeah. Okay, I gotta figure this out.
Okay.
Sorry.
It's pretty fine though. I mean,
yeah.
Maybe if you just take the sock off the mic, then it should be. Well, so it looks like we have a guest lecturer today, or no. I don't know how you want to be called. A jonovision promised that he's going to teach us number 8 collab today. So I'm super excited about that because that means I might not have to type, or I'm just going to type whatever I'm told to type. You know?
Yeah, I think it's
Good
going to be the
execution.
It's going to be the same as me, just in the chat, but just audio.
So
all right,
time.
that's easier.
At least
no lag.
remove the lag. Yeah.
Yeah.
You did do this lesson already, right? Like you already went over
I did it
parts of the course.
I did it a few days ago.
Cool.
I just have to...
I'll let you think. Sonic, what do you think about this situation?
My only concern, which I just realized, is I don't know if I renewed my Zoom subscription.
So because we're 3 people, it's gonna
we'll find out.
Be like alarm.
Yeah, it'll say like 10 minutes left, and then at that point I'll just renew it.
What do you think about that?
Hear me? Is it better now?
Maybe.
I mean, you sound fine. Yeah, could hear you.
You sounded fine before.
Yeah.
Sound fine now.
Does it sound different or no?
I think a
good
little
question.
bit.
Okay, whatever.
I am
That's
no
good.
audiophile.
So, jonovision, before you kick this off, what do you think to the amazing coincidence that both... Oh, hello.
Yeah,
Hi.
There you go.
Nice to meet you.
Nice to meet you. Yeah.
Yeah, it's nice to see
Envision.
you guys. Nice to have you guys see me, I guess.
Yeah. I was just gonna ask you what do you think about that? By coincidence, both me and Nick are wearing plaid shirts today.
Just a sec. I gotta close the window down.
Comment.
It's like
Okay.
bald spot.
Oh, you guys are both wearing plaid. Oh, I could have done that too, but
No, it would have had to be coincidence. So it's all good.
okay, yeah. So I am, just for full disclosure, I am no expert in this at all. I'm just the guy who just pretends that he knows what he's doing in the chat log. And I will just give you guys some pointers, I guess, probably the best way to describe what my contribution would be.
Cool.
All right. Let's do it.
So you're thinking that we just go over the lesson as we do usually, and you're just joining on that, or do you want to lead it and just show us what you did?
I'll follow you guys' lead.
Okay.
I don't want to take over the stream, you know.
No. I was kind of looking forward to that today.
Martin was gonna like
All
chill.
right.
He's gonna lay back.
Fine. I'm gonna be the typist. It's okay.
All right, Martin, get to work.
I am. I already loaded it up, so it's all good.
Cool. All right, so collaborative filtering. Is what
Yes.
we're doing
Oh,
today.
sorry.
We're doing a deep dive. All right.
All
All right.
Well, you're the specialist on that, right, Nick?
Yes, as you can see.
We're all collaborating on this.
Mm-hmm. Three.
I have enough tanks for us to all dive deeply as well. All right, bad jokes out of the way. Collaborative deep dive. One very
You
common,
start, Nick.
I will start. One very common problem to solve is when you have a number of users, a number of products, and you want to recommend which products are most likely to be useful for which users. There are many variations of this. For example, recommending movies such as on Netflix, figuring out what to highlight for a user on the homepage, deciding what stories to show in a social media feed, and so forth. There's a general solution to this problem called collaborative filtering, which works like this. Look at what products the current user has used or liked, find other users that have used or liked similar products, and then recommend other products that those users have used or liked. Okay.
Yes.
It
There's
felt
this
like a
bad
weird
joke about
circle
that.
there.
Yeah. Do you know this joke about how only software developers and drug dealers call their customers users? Anyways, there's a lot of using in there.
For example, on Netflix, you may have watched lots of movies that are science fiction, full of action, and were made in the 1970s. Netflix may not know these particular properties of the films you have watched, but it will be able to see that other people have watched the same movies that you watched, also tended to watch other movies that are science fiction, full of action, and were made in the 1970s. In other words, to use this approach, we don't necessarily need to know anything about movies except who like to watch them. Except who likes to watch them. Who like?
Or liked.
Who liked?
Is it present? Is it past?
There's actually a more general class of problems that this approach can solve, not necessarily involving users and products. Indeed, for collaborative filtering, we more commonly refer to items rather than products. Items could be links that people click on, diagnoses that are selected for patients. That's interesting, and so forth.
Well, if you have a certain type of like symptoms, and then a lot of doctors recommend for those specific symptoms this type of treatment, I guess. Diagnosis. It's the same thing as people clicking on links, right?
Yeah, but the diagnosis for selected patients, I don't know, something about that just makes it seem very like WebMD-y. Like, anyway, the key foundational idea is that of latent factors. In the Netflix example, we started with the assumption that you like old action-packed sci-fi movies. But you never actually told Netflix that you like these kinds of movies. Netflix never actually needed to add columns to its movies table saying which movies are of these types. Still, there must be some underlying concept of sci-fi, action, and movie age, and these concepts must be relevant for at least some people's movie watching decisions. For this chapter, we're going to work on this movie recommendation problem. We'll start by getting some data suitable for a collaborative filtering model. Cool.
Yippee. Take a first look at the data. We do not have access to Netflix's entire dataset of movie watching history, but there is a great dataset that we can use called Movie Lens. Click. Look at Group Lens, Movie Lens. Here it is. Group Lens Research has collected and made available rating data sets for the Movie Lens website. Click. Non-commercial personalized movie recommendations. Okay, I see. So this is where all the free work of many, many people then gets transferred into lots of money for big companies. This dataset contains tens of millions of movie rankings, a combination of movie ID, a user ID, and a numeric rating. Although we will just use a subset of 100,000 of them for our example. If you're interested, it would be a great learning project to try and replicate this approach on the full 25 million recommendation dataset, which you can get from their website. The dataset is available through the usual fast.ai function. So this means, wait, I think we learned this last time that now we're moving on to different types of data, right? Like we're not going to do image recognition anymore. Is that right?
Yeah.
Yeah. Awesome. So we're doing recommendation text-based. Or is it not? Not even. It's just gonna.
It would be like tabular, so like in a chart, basically.
Okay, so that
like,
that falls
values.
under tabular data. I see.
So like values in a chart, basically.
Yes. The dataset is available through the usual fast.ai
Fun
function. That stuff. Let's do it. Import. ML100K.
Movie lens.
Or Martin Luther 100 King.
Or machine learning.
Or machine learning. What's the K though? What's 100K? That's your starting salary when you finish the course.
Yeah, exactly.
Okay. Antar data. Nick, we still didn't do that fix, huh? That maybe is just a total screw up of the code because we honestly have no idea what we're doing, right?
Yeah.
Yeah. Okay. According to the README, moving on, the main table is the file u.data. Where's the README? Is the README over here? There it is.
That's sketchy.
It's just normal HTML. Don't be so CSS heavy in your mind. Doesn't say anything about u.data in here. u.data, file u.data. Find u. Oh, I found it. Okay. It is tab separated and the columns are respectively user, movie, rating, and timestamp. User, movie, rating, and timestamp. Okay, since those names, I see, tabular. Since those names are not encoded, we need to indicate them when reading the file with pandas. Here is a way to open this table and take a look. Okay, pandas read CSV, path, u.data. So where's our path? So this sits again. Sorry, I just like to always go into this weird file system for some reason. So this should sit, no, it must be one level up. Is this the thing that we can't see because it's hidden?
It's like .fast.ai or something.
Right, is it?
Or .root or something.
Yeah, /root / and then it's hidden in there, I see. But should be somewhere in there. They have this path.ls anyways. Can you pretty print that? I'm just wasting time. I'm sorry.
You could go ahead, double question mark it, do .pretty, go do your experiments.
Double question? What?
Yeah, remember the double question mark from like we tried to.
I do remember something there, but I just wanted to do this to see where it puts it into so that we can read it like a number ls output. It doesn't do that, huh? Well.
Anyway.
I'm sorry, guys. Okay, here it is. u.data. There it is. There's a lot of other stuff in here, huh?
Yeah.
u3.test, ua.test, mku, sh, .base. What's .base? .genre? They've just made up nice, funny. They just made up some. Okay, file extensions. Okay, ratings head. Did I run this already?
Cool.
We're fetching u.data. It's tab separated, no headers, and then we're making our own headers. User, movie, rating, timestamp. Okay. Although this has all the information we need, it is not a particularly helpful way for humans to look at this data. magic angular braces show the same data cross-tabulated into a human-friendly table. Wait, what?
Okay, so we have, hold on.
Oh,
The user ID.
I see.
And yeah, you can
How's
start
that
seeing.
how's that human-friendly?
So you have the user ID, movie ID, and you can start kind of seeing where there's like piles of like these different ratings, right? Like these groupings.
So the user 14 thinks movie 27 is 3 good and 49 is 5 good.
So in this case, you have 14 and 293 giving 27 both a 3. But then
293, there it is.
yeah, but then 57, somebody that 293 gave it a 4, the other person gave it a 1.
So do they have the same taste in movies?
Well, then you get like it gets a little closer, right? With 72, 79 is the same, 89 is kind of closer, 99 there's a little bit difference, 143 there's a little difference, 179 there's there's no difference.
But so do you think that user 293 would actually really love movie 49, considering of the limited information?
Thankfully, we can let the computer decide that, not have to do this ourselves.
Right. Okay, we have selected. I'm taking your hint. We have selected just a few of the most popular movies and users who watch the most movies for this cross-tab example. I want to know what this movie is.
Let me know.
What is 49?
Me to read at all? I don't know. Like I feel a little.
Oh
bit
yeah, you're
uneasy.
very welcome to.
Like I don't like reading, but
No. So you're here. So if there's anyone watching, jonovision's here completely voluntarily. I just want to say that we didn't force him to get on the stream.
I'm not getting paid for this.
And he's also not like, we didn't abduct anyone or any sort of knives on throats or something like that. So what I'm trying to say with this is, if you want to read, you're very welcome to. If you don't like reading and you don't want to read, then just don't read, whatever you want. But you're very welcome to join in whichever way you want to. That's what I'm trying to say. Yeah. So you can raise your hand or you can just start reading.
Contribute code to the chat, by all means. Anything.
Yeah, maybe I'll join the chat as well if there's anyone in there.
Martin, do you want to?
It's pretty empty.
Do you want to go down that little path and figure out what movie 49
Which one?
is?
I don't think we have we do have. No, we don't have any names. So I think they don't even have any names.
Could you check?
I mean, maybe
Movie Lens?
it could be.
It could be. If you go down further, they
resolve them.
Two different ones together, and then there is a name.
Cool.
All right.
So
go ahead, Martin.
Me?
Well, or whoever.
We have selected just a few of the most popular movies and users who watch the most movies for this cross-tab example. The empty cells in this table are the things that we would like our model to learn to fill in. Those are the places where a user has not reviewed the movies yet, presumably because they have not watched it. For each user, we would like to figure out which of those movies they might be most likely to enjoy. If you knew for each user to what degree they liked each important category that a movie might fall into, such as genre, age, preferred directors and actors, and so forth, and we knew the same information about each movie, then a simple way to fill out this table would be to multiply this information together for each movie and use a combination. For instance, assuming these factors range between -1 and +1, with positive numbers indicating stronger matches and negative numbers weaker ones, and the categories are science fiction, action, and old movies, then we could represent the movie The Last Skywalker as Last Skywalker, last NumPy array. So wait, what were the things? I mean, these factors.
So this is just like an example. It'd just be like the first one would be how science fiction-y like the movie is, and then the middle one would be like how action-y, and then the last category would be like how old. So I'm guessing Last Skywalker. I'm guessing Last Skywalker is a fairly new movie. I don't really know. So that would be like a -0.9, so it's not very old. And then the first two categories would be like follows the science fiction and action attribute, basically.
Cool. It's a little more science fiction-y than it's action-y. And pretty new. Super. All right. Here, for instance, we're scoring very, there it is, look at that. Very science fiction as 0.98, very action as 0.9, and very not old as minus 0.9. We could represent a user who likes modern sci-fi action movies as user 1. All right. Fair enough. Likes science fiction, likes action, likes new stuff, or relatively new stuff. Yeah. And we can now calculate the match between this combination user times Skywalker and then make a sum. So these are, okay, so this is again one of those, no, this is an array operation now where we're doing times each item times the corresponding item. Is that right?
Yeah.
Cool. And then we're just summing everything that's inside there, like all that. Yeah. Yes.
Yeah. So we're getting the dot product.
No, I don't think so. You don't really have a. Is that still a one-dimensional dot product? Is that a thing?
Yeah. If you read the next sentence, it will say.
When we multiply two vectors together and add the results.
Go ahead, Jonovision. You read something.
When we multiply two vectors together and add up the results, this is known as the dot product. It is used a lot in machine learning and forms the basis. Okay, yeah, that thing screwed me up there. Forms the basis of matrix multiplication. We will be looking at a lot more at matrix multiplication and dot products in whatever.
Open close brackets.
It's hard to.
Go ahead, Martin. Could you want to just read the dot product and make sure that you understand what this jargon is?
What?
Okay. Shade of doubt.
Jargon dot product, the mathematical operation of multiplying the elements of two vectors together and then summing up the result.
Okay, there we go.
Thanks.
All right. On the other hand, we might represent the movie Casablanca as not very science fiction-y, not really action-y, and pretty old. Okay, that's the user 1. There we go.
User 1 would not like it. Since we don't know what the latent factors actually are, and we don't know how to score them for each user and movie, we should learn them. Okay.
Okay, so the latent factors are those three initial factors, right? Like that, what we're setting for this user. Okay.
Yeah.
Mm-hmm. And here we made them up just as an example, and now we're gonna learn them instead.
Okay. So,
and we're not even gonna know. So I guess we're not even gonna know what they are. They're just gonna be some numbers that the machine learning algorithm decides are factors, I assume.
And
we're not defining what they are.
So it's going to, I think initially, right, it's like we don't really need to know like the genre or anything of these movies, but there is, I'm assuming when we scroll down a little bit, there is like another file that kind of
I like this table.
All right, I'm just gonna keep quiet and we can read.
There's so many fields. All right.
All right, there's a surprisingly little difference between specifying and the structure of a model as we did in the last section and learning one, since we can just use our general gradient descent approach. Okay, step 1 of this approach is to randomly initialize some parameters. These parameters will be a set of latent factors for each user and movie. We will have to decide how many to use. We will discuss how to select this shortly, but for illustrative purposes, let's use 5 for now, because each user will have a set of these factors and each movie will have a set of these factors. Each user will have, okay, so each user has a set of these factors and each movie has one. Got it. We can show these randomly initialized values right next to the users and movies in our cross tab, and we can fill them in dot products for each of these combinations in the middle. For example, dot shows what it looks like in Microsoft Excel with the top.
Nice.
Yeah.
I get it. So you get the user, those are the factors for one user. No, those are the factors for one user. Those are a couple of users. That's the factors for a movie. Those are a couple of movies. Zip, 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 zip. And then we're just doing this multiplication essentially in the same way that we did it further up. Yeah.
Okay, so we're using 5 values.
Mm-hmm. We're going to do this times this times this times this.
Initialized
Not plus,
randomly.
I mean,
and then we optimize them with gradient descent. Okay, so
Distance
like these
this
values
plus
don't,
distance this.
they don't mean anything, right? We're just randomly selecting values here.
Yeah.
And is there a range? Like I'm seeing.
I think it's -1 to 1.
No, because I'm seeing some are 2. Maybe if
I-
we
Where?
scroll
I
down,
just
scroll down a little bit. Maybe there's like a 5 is the highest, maybe, or something.
I don't
Well, no,
know.
it's
I
just.
don't know if it's sorry.
No, you go ahead.
I don't know. I don't remember reading anything about like specific range. If I would guess, it'd probably be like a normal distribution around maybe like 0 or 1. I'm guessing.
Yeah, but we're getting some that are like in that first column, right? We got 2.39.
What
the
what
first
are you
column.
talking about?
So
First column.
Movie ID right
Yeah.
above the number 27.
Ah, you're right.
We have
Yeah, I see.
the ranges from minus 1.69 to
Mhm.
positive 2.39. So I don't know. Maybe like in the code later on, it'll. I don't know because we kind
Yeah,
of.
it might. Yeah, the initialization, it might say exactly how it gets those numbers, but yeah, I'm not 100% sure.
Okay. So yeah, and it starts with randomly initializing them.
Yeah.
I
Okay.
see. Yeah.
All right. So step 2 of this approach is to calculate our predictions. As we've discussed, we can do this by simply taking the dot product for each movie with each user. If, for instance, the first latent user factor represents how much the user likes action movies, and the first latent movie factor represents if the movie has a lot of action or not. The product of those will be particularly high if either the user likes action movies and the movie has a lot of action in it, or the user doesn't like action movies and the movie doesn't have any action in it. On the other hand, if we have a mismatch, a user loves action movies but the movie isn't an action film, or if the user doesn't like action movies, okay, the product will be very low. Step 3, calculating our loss. We can use any loss function that we wish. Let's pick mean squared error for now, since that is one reasonable way to represent the accuracy of a prediction. That's all we need. With this in place, we can optimize our parameters, that is the latent factors, using stochastic gradient descent, such as to minimize the loss. At each step, the stochastic gradient descent optimizer will calculate the match between each movie and each user using the dot product, and will compare it to the actual rating that each user gave to each movie. It will then calculate the derivative of this value and will step the weights by multiplying this by the learning rate. After doing this lots of times, the loss will get better and better, and the recommendations will also get better and better. To use the usual you learned that fit function, we will need to get our data in the Dataloader, so let's focus on that. Okay, so creating the Dataloaders.
So now we're going to see how to do the Dataloaders for tabular data. Probably the same.
Yep, seems like it.
When showing the data, we would rather see movie titles than their IDs. You know me. The table u.item contains the correspondence of IDs to titles. Okay, so now here we go. Movies, read in user u.items. They have a different delimiter because why not? Encoding. I wonder why. It's not that like a movie title would have a tab in it. Usually, it's more likely that a movie title would have this character in it, right? Than a tab. I don't think I've ever seen a movie title that had a. Am I making sense? No.
Yes.
No. Okay, so this is not important. So let me talk about it. Because they're choosing different types of delimiters, right? The other one was a tab separated one. Scroll.
Yeah, it
Isn't
was.
there a way to like escape those as well? Like, can't you escape a pipe character? So like if
Probably.
it actually exists in the movie title, maybe they just changed the movie title to escape that.
I'm just saying, why not use a tab? Because there's probably no tab in a movie title.
I don't know.
Yeah.
I have no idea.
I don't know either, but it's more likely there's a pipe in there. I'm sorry. Pandas read CSV, item, delimiter, blah, encoding Latin, use columns 0, 1. I guess there's more than these columns, and we name the movie and title. No header, but we're adding our header. Okay, let's look at it. Movies.head, and finally we can find out what movie with the ID 49 is. Does that work? Let's see. Wait, we're 0 is 1, so that would be ID 48. Cannot. Movies. Oh, yeah. How's this index.idx? Is that it?
Might be iLock.
iLock, that's how it is. Lock. No.
No.
What does it say? No.
So no, it's something like that. It's I think iLock is. So iLock goes for.
Oh, go okay, go up, scroll up.
Axis name. It looks for the axis name. So that would use for movies.
So it should have 49.
Go. What's the data frame called? Go up.
Movies.
Okay, movies.movie.
And then we can do that.
And then.
Do we have to do iLock or just 48? It should work with that.
Try
if it's
without. Yeah, try
yeah,
that.
if it's a series.
It's just gonna return back 49. It's just
40.
So just like do the dot. Can you do like
I should
title?
know this, but I can't.
Wait, no, hold on. Change movie to
Just
title.
go movies.head and then go 50 and then scroll down.
Hold on. Yeah, just change that. Remove the front
that's-
part, and that's it. And
That's
then you have
easier,
the
but that's
title.
gonna.
It's
yeah,
gonna
that
give you the
makes
title
sense.
of 49.
Of 49.
Yeah. IQ.
IQ. I never heard of this movie.
All right, let's look it up.
See what it's rated.
This person really liked it though, or am I missing it? 49. Yeah, 49. They really liked it. Intriguing. What's that?
IMDb.
IMDb. IQ 1994. There it is. Fred Schepisi.
We should play a little bit of the movie so then we can lose
all the
what is it?
income.
We can't make money on it. We put it on YouTube.
Right. Oh, I know this movie actually. Does any of you know this movie? It's like some romantic comedy from, I guess, 1994.
Yeah, no.
I think he's like kind of like or no, she. I don't know. One of the two of them is some nephew or grandnephew of Einstein. It's not great.
6.2 out of 10 on this, but somebody
6.2 out of 10. Yeah.
We also didn't
So-
see how does that.
Wow,
Yeah,
Meg Ryan's in it.
Mm-hmm.
Meg Ryan.
And the other guy, I don't know.
I don't know.
Tim Robbins, I'm guessing.
Tim Robbins. Yeah. Okay. So this person, number 14, really liked that movie.
It
Maybe
seems
they're
like
a big Meg Ryan fan.
It seems like a
Maybe.
good amount of people like that movie. Look, 5.
Well, let's see.
5, all the way down. 4s, a 3.
You're right. Yeah, that was pretty highly rated. So wait, so I'm just gonna, I gotta know the movie taste of number 14. So 143 and 92. Let me just see that real quick. I've already forgot them. 92. I remember 92.
So
check that one.
91.
Right. Thanks. I would have probably made that mistake. 91. True Romance. This is a person who really likes romantic comedies, I think.
Yeah.
At least,
Toms.
yeah.
What was the other
Okay.
one? 153?
One more. Let's try one more. Yeah, I don't know.
What was it?
143.
143.
And try one that they scored really low on and see
Yeah,
what they
Good
hate.
idea. 143. Do you have?
140.
Does any of you have that open also? So
No.
that I don't have to scroll back up for the numbers? No. Okay. Sound
The
of.
sound of Okay. They
I
also
have,
Everyone loves that movie.
all right, so what's-
99.
So I gotta admit something about Sound of Music because I'm Austrian
Yeah.
and I haven't seen the movie myself, but it's like one of the things that at least every American, not every, but a lot of Americans that I meet, they know and love the Sound of Music, and that's like the one thing to know about Austria. Not the one thing.
yeah,
I'm generalizing. I apologize.
Look up, what was it?
57.
57 and 99.
Okay.
Because we got two pretty low ones.
57, 99.
Probably like Die Hard or something.
Like the Fast and Furious movies.
Well, no one likes those movies.
I actually haven't seen a single one, so I can. Priest. I don't know that.
98.
Maybe they're an atheist.
Sound of Music, True
Snow
Romance,
White.
IQ.
Wow. Oh, no, 99.
Yeah, but it's
99.
98 because it's 99.
Yeah, we could just get
that's right.
next one. Priest.
They also scored another one that was a 2. Just curious.
2011, no, 1990. What was it? 1994?
Yeah.
Was it? Yep.
There it is. Linus Roach. A homosexual Catholic priest finds out during confessional that a young girl is being sexually abused by her father. And that's how to deal with both the secret and his own.
This one scored higher.
That sounds interesting.
That sounds interesting. So I guess maybe I don't really agree that much with the movie taste of this person. Snow White and the Seven Dwarfs, one of my favorite. I haven't seen it actually.
What movies have you seen?
I have seen IQ 1994.
And True Romance, maybe.
I'm not sure. I might have. I don't know what that is actually.
Only movies that have dealt with Einstein, I'm guessing, is what you've seen.
Christian Slater.
Christian Slater? No, I have not seen this movie. I don't think so.
Wow, it's got a good review.
7.9.
Oh, Quentin Tarantino did it.
7.9. Oh, interesting. Britain. Yeah, never heard of it.
All right.
Does it say crime, drama, romance? Crime, drama, romance. Typical Quentin Tarantino. Okay. I'm ready to move on. Do you guys want to anything else?
Good. I'm good to move on.
Okay. All right. What's the read?
We can merge this with our ratings table to get the user ratings by title.
Okay, let's do it.
So you're just merging, two ratings with movies.
Mm-hmm.
And they have a common column, I believe, which would be users or no?
So what does it do? Does it do like a left join or whatever it is?
Inner join, I think.
Inner join. So we got user and movie. Both of those IDs exist in now. Movie ID must be the one they're joining on, right?
Yeah, it's movie rating timestamp name on all of them, and then it's just changing by user. So the user ID column is the only thing that's actually changing on this one, right? So it's grouping them by scroll down.
Wait, I don't think that's right. Where do you see that?
Yeah, look, I mean, it's just ordering them here for all the same movies, and then for each movie, right? Colia, this user gave it a 3, 63 gave it a 3, 226 gave it a 5. Yeah.
No, but the frames we're merging is movie ID. That's what we must be merging on because that's in both of the tables. Yeah. The one has movie and title, and the other one has user, movie, rating, and timestamp.
I don't know what this timestamp is. That like when they gave it the rating? Because all these timestamps are different for the same movie.
Yeah, I would think so.
That would be my guess as well.
All right, I'm gonna go get some cookies.
All right, jonovision, you keep reading.
Okay. We can then build a Dataloaders object from this table. By default, it takes the first column from the user. I guess this is explaining what we just tried to figure out. The second column for the item. Here are movies. And the third column for the ratings. We need to change the value of item name in our case to use the titles instead of the IDs.
Item name. Okay. Okay, so now we're actually creating the data loader and collab Dataloaders. So that's a completely new class that they're using for that, huh? For a tabular data loader.
New fast AI one that we haven't really seen yet.
Look, Nick, new type of data loader, the collab data loader. I honestly thought that when I read that the title of this exercise is collab, that it's going to be about Google Colab. But it's got 2 L's in there, and
we learn about it 8 lessons in when we start using it in lesson 1.
Because it's optional. You could like use something else. I thought maybe there's like some deep dive, finally explaining the folder structure or something. Oh, I assumed around. Okay, collab. So is that a thing? Like, I'm totally lost. Where are we? Here. Okay, is collab like, does that mean tabular data, or is that a term for that?
I think it's just collaborative data loaders, right? That's what we're doing.
Yeah. But collaborative with what? You don't have an answer for that, huh?
Well, I mean, what do we?
You can kick me off. I'm sorry.
Go to the second tab. Go back.
All right, chill.
Scroll all the way up.
All the way up.
All the way up.
You don't mean that.
I do mean it. All the way.
All the way. Okay.
All the way to the top.
Wait, I thought I clicked go all the way up, but it didn't do it. There you go.
Okay, now scroll down. Very low. Collaborative filtering. That's what I think is happening, right? So we're doing collaborative filtering, and we need a collaborative data loader. And that's all. I get it.
But what is it collaborating with? Is what I'm wondering.
So, I mean, let's learn this. Like,
I think I get it though. It's like just humans working together by giving ratings. Maybe that's the collaboration.
Yeah, I guess. Yeah, I guess that makes sense.
Wait, that's not where we are. Creating the data loaders. Okay. Nick knew it all along, but he was graceful enough to just.
It was the cookies.
Keep scrolling. We did this already.
No, that's where. Oh no, you're right. Okay,
there we go.
Here we are. Okay, so collab data loaders. So this is just for any tabular data where we want to do some suggestions, I guess. I don't know. Run it. Item name title. Okay, so and then we have to, because we want to have the names of the things, we need to define. I guess we have to pass in from a data frame. Ratings is the thing that we wanna predict, right? We want to know how much do people like it.
Yeah, so the ratings was just that data frame that we just made, right?
Oh, okay. It's a data frame. Yeah, you're right. Okay, I see.
Yeah.
Awesome. And then item name. So from the data frame, we look at title to get the names. Okay, and we make a batch size of 64, and then look at one of the batches. Okay. To represent collaborative filtering in PyTorch, we can't just use the cross-tab representation directly, especially if we want it to fit into our deep learning framework. We can represent our movie and user latent factor tables as simple matrices. Classes. This is how they're internally represented in the data loader. We get, I wonder what that is about. Title. So this is maybe no rating? No, that doesn't make sense.
It also seems like it's only on the first one, so maybe it's just 0.
Yeah, you're right.
There's no 0 user. There's no 0 movie.
So it's like a missing.
Yeah, I think it's just right. It's just showing the title and the. Oh no, I don't know what user.
User, that would be the user ID.
Yeah, I never mind. Yeah, I think what I was saying.
So it just counts
There's
up.
no 0 and 0, but they don't map to each other or anything. They're just like showing everything, all the titles and all the user IDs, right?
Simple matrices. How do you actually pronounce it? Because
matrices.
Matrices, thank you. I knew it was wrong.
Or mattresses. You can say mattresses too.
That sounds more comfortable. Okay. Number users, length, Dataloaders, classes, user. Okay. Let me see what you got. If I run you, nothing. Perfect. So number users, length of of this array. So it's counting this one though, if it does the length on that. Right?
Yeah, I would assume so, yeah.
Okay. Maybe we'll see what this is.
Maybe we should find out NA's movie taste.
Okay, how do we do that? Okay, user factors, torch. Okay, PyTorch, random number. Is that what it does? Just making.
Yeah, so I guess if you were to, because we're wondering what range of values that they chose from.
Mm-hmm.
If you did run torch.rand and then 2 question marks, maybe it would tell you what like the default range is. I don't know what it is, but that would be those.
Is that how you do it? I forgot that. Or do you call it?
Yeah, try that, or try without. Yeah, I think it's like that.
Mm-hmm. Nice.
Yeah, so a mean of 0 and a variance of 1. So yeah, normal distribution.
Okay.
Mm-hmm. Mm-hmm. The shape of the tensor is defined by the attribute size, and so it's just making it in the size of the like in the same size as these ones. Wait, so it's a factor. So is this making a multi-dimensional one with the 2 of them?
So that that Excel
5.
sheet like above, yeah,
right.
just makes it
so
look
it's
like
the left bar and the top bar essentially of the 2 of them. Yeah.
Yeah.
Yeah. Can you just print one out? Print out user factors.
Sure. Yeah.
Let's see what it looks like.
Factors. Uh-huh. So, and that's going to be 5. Yeah, 5 per user.
But yeah,
nice.
This does look like a normal distribution, right? Obviously, because it's wait, go back to that definition because you're getting below -1 now. It's not between -1 and 1.
So yeah, so a normal distribution, like, so you know that bell curve. So there'll be more like a high frequency close to 0, and then there'll be like a small amount outside -1 and 1.
So it goes into like it does the normal distribution around 0.
Yeah, I think that's what it said. So yeah, so you can get a 2.4. So that would be like a super
mean 0. Yeah, there you go. Yeah.
Gotcha. Okay.
Let's say curve around 0, and we get a couple of values somewhere out there.
Got it.
Okay. Help.
Cool. Okay.
Sweet. To calculate the result for a particular movie and user combination, we have to look up the index of the movie in our movie latent factor matrix and the index of the user in our user latent factor matrix. Then we can do our dot product between the 2 latent factor vectors. But look up in an index is not an operation our deep learning models know how to do. They know how to do matrix products and activation functions. Wait, what's the problem here? So because we calculate results, we have to look up the index of the movie in our and the index of the user.
So this area gets kind of confusing. I'm not even 100% sure I totally grasp it 100%, but
what do you think is what's your understanding of this? Why would we want to do a lookup and not just munch all the data in there and let it do its thing?
So we want to do like a lookup, but unfortunately when you do that, you lose the gradient. Like you can't do a gradient of a lookup. so an index lookup. So they have to do, so if you do a one hot encoder, it actually does the exact same thing as a index lookup, but you keep the gradient if you do that. So yeah, it's really, I don't know if I could be explaining it wrong.
No, I'm sure.
But yeah, they go through and they show that you can do a one hot encoding as an alternative to doing like an index lookup. So if you wanted like the user 3, what their factors could be, you could use a one hot encoder with the 3, and you would get the exact same as if you did like an index lookup with a 3. But the problem with doing the index lookup is that you lose the gradient.
Interesting. I don't understand it yet, but I'm gonna keep reading.
It sounds
probably
like you're kind of abstracting the lookup through this one encoding.
Yeah.
Right? And you have like this other.
But how does it work with the one hot like? No,
you're almost like like the index of like the gradient, right? Is this 3 for what the index would be for scroll up. What was the original one?
What you're looking at? Further up?
No, scroll down. No, just that like the 2 paragraphs over there when they're talking about it. Right, like from this, what I sort of understand and like what you were describing is like now the index of the movie is just mapped to like the index of a gradient using one hot encoding. Like there's a bunch of gradients, and then 3 is just now the same, right?
So 3 is going to be a number between 0 and 1. That's just a linear one hot encoded thing for all the user IDs.
Say that again.
Is 3 just, so if it one hot encodes all the user IDs, right?
So if you wanted like the 3rd user, you would do like a one hot encode with a 3. So then it'd be like all zeros for all users except for like index 4, I guess. So it'd be like a 1 there. So then you would so it would only return the user factors for that. Yeah, so the 4th one there.
Okay.
So they would use this technique to get that like index lookup because it would keep the gradient. But unfortunately, I'm fucking skipping. Oh, sorry, I said the F word. So they use this as a way to keep the gradient.
This means we can't monetize the video.
I was like, hey, I have to not swear when I'm on here. Okay. But for stream.
Have either of you watched that like History of Swearing with Nicolas Cage on Netflix?
No.
There's like it's like the history of swear words, and every episode is like how they were derived and like where they came from. It's really interesting, but yeah, definitely recommend it because obviously Nicolas Cage just like cursing on television is the most wonderful thing you can imagine.
Yeah, I'll have to check that out because my wife is French, and all their swear words, they're all like church words. So it's like really interesting. There's Jim Gaffigan has a bit on, I think it's YouTube, because he was posting a whole bunch of stuff during the pandemic about like French word, or it might have been Canadian, something about like Canadians or French swear words. I don't really know exactly, but yeah, it's pretty funny. I would not be able to describe it, but yeah.
Interesting. Trying to process something in the French psyche.
Yeah, they're like they're all French. They're all French nouns. Sorry.
Interesting.
Okay, I think I kind of understand this.
Yeah, me too. I was just thinking about German swear words. But I guess no need. Yeah. Okay, I get this too. I think makes sense. No. And then .t. What are you?
Transpose.
Transpose. Let's double check, but it's probably good. Chat, practice that question mark. Tensor. So make a tensor.
Oh, I guess, yeah.
Okay, so this is taking the user factors, making a tensor at 1 hot 3. So at whatever.
At wherever this is
at
1.
is dot product.
Nice.
Mm-hmm. At is dot product. So the dot product of 1 hot 3.
Cool.
Cool.
This makes sense. All right, that's nice.
So just to kind of like drive the point home for
Do it.
The less intelligent person on this stream.
Me.
Oh, that would be me.
So when you're saying like keeps the or maintain what was it, maintains the gradient or like keeps the gradient or something, this is what you're saying.
So
right?
they will describe it later, but
okay.
Yeah.
Okay. Cool.
You want to give us a preview, or should we just keep reading?
No, that was my preview.
Okay, good. Good preview. Keeps you wanting more. Okay.
So
it gives us the same.
Yeah. Go ahead.
You.
Okay. So it's basically just saying that these are the same. Yeah.
All right.
Yeah.
So this gives the same vector as the one at index 3 in the matrix. So user factor is 3. All right. So that's fine. I'm gonna keep my questions to myself for now. If we do that for a few indices at once, we will have a matrix of 1 hot encoded vectors, and that operation will be a matrix multiplication. This would be a perfectly acceptable way to build our models using this kind of architecture, except that it would use a lot more memory and time than necessary. We know that there is no real underlying reason to store the 1 hot encoded vector, or to search through it to find the occurrence of the number 1. The number 1 I don't know.
The number 1.
Yeah. We should.
That one. There it is. Look.
Thank you.
No worries. You can always count on me for useless scrolling.
Nick, or we should have a segment where it's Martin learns useful scrolling. Separate.
I thought I was gonna have a seizure earlier with the of up and down scrolling.
Yeah, you should give me that power, but I don't know. I got it.
You got it somehow. All right. No, I did not want to update Java in the middle of a stream. Thank you. We should just be able to index into an array directly with an integer. Therefore, most deep learning libraries, including PyTorch, include a special layer that does just this. It indexes into a vector using an integer, but has its derivative calculated in such a way that it is identical to what it would have been if it had done a matrix multiplication with a 1 hot encoded vector. This is called an embedding.
Okay.
That confused me even more.
Oh yeah.
I feel like
I think it's just
are they it sounds like they're kind of like backstepping and saying like we don't want to do this 1 hot encoded vector anymore.
Yeah. That is correct.
Oh, I understood that it's just like it does the 1 hot encoded vector in the background, but you don't have to explicitly do it. Like it's just you pretend you're indexing, but what it really does is this 1 hot encoding and getting the values like that.
So
the matrix multiplication. Yeah.
Just think of embedding as doing the 1 hot encoding in the background, but it keeps the. Oh yeah. Okay, just think of it as doing like an index lookup, but it keeps the gradient. Or also you can think of it as doing the 1 hot encoding, but it like reduces the amount of memory that your computer has to use while doing it. So it's basically the exact same thing as doing a 1 hot encoding, but it reduces the amount of RAM that's being used by the computation. It's like a computational shortcut. I don't know.
Yeah, because it seems.
So it's not actually. Because
it seems like here they're saying like we don't have to look for that 1, right?
Yeah.
And that's where you're saving that memory, right? Is like searching through this vector for the number 1, finding that index, and then looking up in this other factor vector, right?
Yeah, it's just what Jeremy, I think that's his name. What he said is it's just a simple short, yeah. So that jargon, if you read that, that may help you understand it a bit more.
Multiplying by one hot encoded matrix using the computational shortcut. Using the computational shortcut that it can be implemented by simply indexing directly. This is quite a fancy word for a very simple concept. The thing that you multiply the one hot encoded matrix by, or using computational shortcut, is called the embedding matrix. So you're multiplying the one hot encoded matrix with what?
The user factors and the user factors and the movie factors, I believe.
Okay.
So you can get that dot product. So you're just trying to pull out those. So if you want user 10 and then movie whatever, you would just pull out those two factors to do the dot product.
So this is creating another matrix of just the dot product between the two.
Well, you're doing a dot product, so you get a single value. So you're getting two vectors.
So this embedding matrix is, I feel like I'm confusing myself.
Me too.
Right? Like, is this, so scroll up. I just want to, I think maybe the value.
I thought I had understood it, but now I don't think I understand it anymore.
So that tensor right there, user factors 3, where you have those 5 values.
Yeah.
Is that, scroll up a bit more with that.
I don't know if there's like any physical embedding matrix, if that's what you're trying to think of, because in my mind, I don't have that.
Okay.
I don't know if that's a bad thing.
So the embedding matrix for you is not like a physical thing, but it's more of like the concept and like the what's it called? Like the way of doing it, right?
Yeah.
So this one seems, I don't know.
Yeah, it gets a little like this part definitely messed with my mind a little bit, but I don't know. I feel like I kind of have a grasp on it. Like I'm definitely not Jeremy Howard level of understanding, but I feel like I can fake my way through it, like what I'm trying to do right now.
I mean, I think
it's kind of
I don't really understand like I guess I get this part, and then
I don't get why we're doing the one hot encoded for 3. Like I don't fully understand that.
For me it would make sense if that's actually happening also in this embedding somewhere, but you just don't do it explicitly, like you pretend you're indexing, but it really does the one hot encoding and gives you the values back. That would make sense to me, but from your discussion now, I got the impression that that's not happening.
Well, I'm fully, I think that is kind of what's happening, and I'm okay to kind of move forward and just accept that, but I just don't understand why that's why it's even happening. Because right now I'm looking at just from like a syntactic perspective, right? Like user factors 3, and you return back this tensor. So what I kind of understand is that user factors is just a tensor of tensors, right? But,
so matrix,
yeah. So is user factors this embedded matrix? And then if we're just looking it up by index, what's the point of looking it up this one hot encoded thing and then coming back? Like I just don't,
because you're losing the gradient.
Oh yeah.
Maybe I don't know what that means.
We'll see.
Like, well, because you need the gradient in order to do like a gradient descent. So you want, because we're trying to limit the loss, right? So we need like everything that we do computation on, it has to take into account the gradient. So you need that gradient in order to calculate the loss, and that's why you have to do the one hot encoded of the user factors and the movie factors.
I mean, I'm assuming it's a very clever way of doing it that maybe I wouldn't have like gone this, like if I was presented this problem to come up with this sort of solution to like
I definitely would not have thought of it either.
Yeah, and I think that's just what's messing with my head, is that I don't fully understand why this works, and I'm willing to accept that it's clever and move on.
I have another thought about it though. Jonovision, do you know why it loses the gradient if we would do the lookup? Like what does that actually mean? I understand that's the problem, but
I just accepted that it lost the gradient. I don't know exactly.
Okay.
So,
yeah. Okay.
Like what I've learned.
Fair enough.
I've learned from learning computing programming is like you just have to accept it sometimes.
Yeah.
I think that's what is holding me up too. Is like, why is it losing, or how is it losing the gradient? But
yeah.
Anyway.
I mean, my assumption is kind of like that the index lookup always goes to the same spot or something.
Yeah.
And then. But at the matrices, maybe they can change their little numbers that are in all the different cells. So I don't know. I don't really know.
But yeah, I'm just guessing like someone figured out like you can't get a gradient of a like looking up a certain value in a matrix. But I guess it stays if you do a one-hot encoding. I don't know why. But
I sort of get it, and I feel like and maybe I don't know, but the way that I'm kind of like, I can sleep well at night is to think of this one hot encoding as this like, almost like a lookup table abstraction.
Yeah, basically that's all you have to look at it as, basically.
Okay. All right, whatever, moving on.
All right, I'm gonna take this. In computer vision, we have a very easy way to get all the information of a pixel through its RGB values. Each pixel in a colored image is represented by 3 numbers. Those 3 numbers give us the redness, the greenness, and the blueness, which is enough to get our model to work afterward. For the problem at hand, we don't have the same easy way to characterize a user or a movie. There are probably relations with genres. If a given user likes romance, they're likely 14. They're likely to give higher scores to romance movies. Other factors might be whether the movie is more action-oriented versus heavy on dialogue, or the presence of a specific actor that a user might particularly like. I wonder whether it does like, because it says heavy on dialogue. Yeah, I guess it does. I was wondering whether it does like amount of words spoken.
No, it's just literally all random, and I don't know, just.
Yeah.
I was just realizing that this doesn't make any sense because it's not analyzing the content of the movie. Actually, it's just analyzing what people think about it.
Yeah.
Is there like, I mean, maybe we'll find out later, but is there like a sweet spot for the number of factors that you want to kind of include, where like too many you get negative effects, or like you get this like weird recommendation if there's like, I don't know, like 30,000 factors versus like, 20,000 or 10,000 were like the right amount.
What would happen? That you overfit? That it just shows that one specific movie, or what? If you have too many factors? What?
We think you're gonna like this movie. It's like, yeah, I know. I rated
That's the one. I just rated.
Anyway,
yeah, it doesn't make sense.
Moving on.
Okay. How do we determine numbers to characterize those? The answer is we don't. We let our model learn them. By analyzing the existing relations between users and movies, our model can figure it out itself, the features that seem important or not. This is what embeddings are. We will attribute to each of our users and each of our movies a random vector of a certain length. Here, number factors 5. And we will make those learnable parameters. That means that at each step, when we compute the loss by comparing our predictions to our targets, we'll compute the gradients of the loss with respect to those embedding vectors and update them with the rules of stochastic gradient descent, or another optimizer. At the beginning, those numbers don't mean anything since we have chosen them randomly, but by the end of training, they will. By learning on existing data about the relations between users and movies, without having any other information, we'll see that they still get some important features and can isolate blockbusters from independent cinema, action movies from romance, and so on. We are now in a position that we can create our whole model from scratch. Cool. All right.
Collaborative filtering from scratch. Before we can write a model in PyTorch, we first need to learn the basics of object-oriented programming in Python. If you haven't done any object-oriented programming before, we will give you a quick introduction here, but we recommend looking up a tutorial. Okay, the key idea of is the class. We have been using classes throughout this book, such as Dataloader, string, and learner. Python also makes it easier to create new classes. Here, example of a new class. You know, I feel as like someone who's never written a Python course, I feel like from the 3 people in this stream, I'm going to speak for myself, but I'm probably the least qualified to teach Python here, because I think we do have
I've only I just started learning Python just like a year ago, so I'm pretty big noob.
Yeah. Martin, on the other hand, has written courses in Python, multiple. So
shut up.
If you want,
never would have thought.
If you want to take it away.
Why should I just?
You hear that, Martin? You would have never thought that you wrote courses in Python.
Thank you. Appreciate it. I can read this if you want. The most important piece is a special method called init. See, and I was just like, oh, let's just skip this. Such obvious information, everyone knows.
Put your own little flair on it too. You could just ignore you explain this code block in your own words.
Yeah, explain object-oriented programming to me.
Yeah. Okay.
To us.
There you go. This is practice for you.
Without looking at the screen, just off the top of your head.
This stream turned into, from me thinking that I'm gonna not have to do any work, into something completely different. I'm just saying.
Consider this practice for your real teaching screen.
Okay, guys. Sure. Okay, so a little lesson on classes. Let me try. I mean, I guess both of you know, like, object-oriented programming, just not Python specifically, right? Or
yeah.
Well,
yeah.
I mean, I don't know.
So what am I gonna do? There's the Python has this specific thing called the dunder methods, which is just semi-private methods in a class that you're not supposed to change necessarily. I mean, that are called in specific situations. So I get, like, the most common ones are this init for when you make an object. So if I'm gonna want to make a class example, I'm gonna say this, call it, and then this calls the init function in there. So that's what init does. It just, when you construct the class, it calls this constructor method. And then there's some other ones, like this one, that you can decide what gets printed when you call print on an object of the class that you're creating. So I could say, instead of printing anything, you just say hello. And self in Python is just a reference to the instance itself that you're passing around in Python. I think JavaScript does the same with this. Mm-hmm. And I'm sure other languages do something similar too. So if I run this, what's going to happen? If in our class example here, what's your guesses?
Nothing. I don't know.
Mick, you got a guess?
Okay.
Or it might say hello. I don't know.
No, I don't think.
Which methods it's gonna call?
I think it might say just hello or nothing. I'm not sure though.
No, it's not gonna do. I wasn't listening to, like, the dunder string method. I don't think it's gonna, I think it's no. I think it's just
did that to confuse you.
I think it's just gonna do nothing. And then when
it's gonna
pass, like,
it's gonna return an error because we want.
Oh, you
gotta
pass
something. So what it does, it wants to run the init method. That's the constructor, but the constructor requires, additionally to just having a reference to itself, it requires an input. So we need an argument here that we want to assign to something, right? So if I just call it without anything, I get an error. If I pass anything in there, like, for example,
it's not going to do
that. Yeah, my legal first name, yeah.
Then it's going to be fine. So now it created the object. And now I have this now I can call the different methods on it that I have defined in here, which is, it's mostly this one, right? Like that's a method that takes, so how would you call that? Any guesses?
Dot say or no?
Let's
Or
say,
no,
and
no.
anything
You
else?
would go you'd go E, wouldn't you go E bracket and then whatever you wanted to say?
Like this?
Whatever X would be, yeah. Yeah, I believe.
What's E
And
right
put
now?
E's that, right?
E is just
So
an
E-
Or,
object.
no.
It's just an example.
I don't know.
E is an object, like, yeah, E is an instance of the class example. So it has access to this.
Oh yeah, E dot say, I think, right?
Yeah, right. E.say. And then if you actually,
Yeah, pass something in there.
like
right,
a string,
otherwise
I
you're gonna have
guess.
the same thing. Otherwise it's gonna fail again because it needs a second input. So yeah, you can do. How are you?
Now, how do you set optional parameters in
Right. So
Python?
now we just get this string output.
So how can I?
That uses the. Sorry, let me just. So it uses this. What we used when initiating the object, we defined this thing here, which got assigned to self.a, which is not a very descriptive name here, but you can use it anywhere inside of the class by referencing to it with self dot whatever it is. And then the second thing is just the argument input that we have that gets then printed out here. So what did you want to say, Nick? Sorry for.
No, I was just saying. So now, how do you go ahead and change that say function to have an optional X?
The self function?
Yeah, the say function. So say, let's say I just want to say. So say I want to have that say function. Yeah, there you go.
So we could do something like that.
Yep.
Where we say it's nothing, but you can if you want. I mean, this is a bit more. Right, we're gonna have to do something like that. If greeting, then we can.
Can you not just pass greeting over there? Will
Well,
it error out if it's none? If it's
Yeah, true.
It
I guess it's not gonna print anything. True. Should work.
No, my question
Would
is,
look nicer though.
will it print out anything if it's none?
Yeah, no, I don't think it does.
Can you run it without?
So it's just gonna be empty. So this should still work. And well, we're gonna have to pass it. No, we don't actually have to. Yeah. But if you call it without, I should have an empty thing.
It should work. Yeah.
Oh no! Look, it
Sure,
converts it to a
no.
string. Yeah, that's f strings. Yeah, it converts it to a string. So that's not.
not
So
a
it would
string.
make more sense in that case to go if greeting, then you want to do this, and otherwise you could just return a string without it.
And there's no way to just have. Can you set instead of none for greeting, set it as like an empty string,
Yeah, that would work.
and then that would print, and then you could remove the if else, right?
Mm-hmm.
Is
Yeah.
that like not really like Pythonic? Like, is that not something that you would normally see, setting it to an empty string? Because I feel like
No, it's fine.
Really, I've always seen like the setting it to none, or
I don't know.
anyway, whatever.
No, it's fine. Yeah. So, anyways, so the dunder string that I put in there to confuse everyone is just what's going to happen when I call print on that object, right? So you can define what you actually see, like what it prints out when you print it. Those are some. Anyways, I don't think this is very relevant, and I don't think this is a good introduction in object-oriented programming in Python that I'm doing here at the moment.
It was great.
Okay, great. So let's move on. Now let's see if there's something interesting in here. Most important piece is the special method called init, dunder init. Any method double underscores like this is considered special, indicates that there's some extra behavior associated with this method name. In this case, init calls it when your new object is created. So this is what we're doing here, right? Talked about that this calls the init method. So this is where I can set up any state that needs to be initialized upon object creation. Any parameters, including when the user constructs an instance of your class, will be passed to the init method as parameters. Note that the first parameter to any method defined defined inside a class itself, so you can use it to set and give any attributes that you will need. This is still gonna work, I think, even though we changed the class. Yeah. Also note that creating a new PyTorch module requires inheriting from module.
Jeremy's ex is named Sylvain.
If what?
If Jeremy's like ex, you know.
Oh no, this is the second guy who wrote the book together. They wrote this book together.
Oh, maybe it's the ex-partner. They're not.
Why do you?
No, I know EX stands for example, but I'm just saying like ex-author. Anyway. Bad jokes are just not landing today. Keep it
just
moving.
tonight.
Keep it moving.
Also note that creating a new PyTorch module requires inheriting from module. Inheritance is an important object-oriented concept that we will not discuss in detail here. Essentially, it's just you get everything that is defined in, like someone made a class called module somewhere, and by inheriting from it, it's going to take everything that's defined in that module class and make it accessible to this new class. And if you have anything that's defined the same, so module probably has also a dunder init method in there. If you define it again in here, it's going to get overwritten. So dot product is going to have everything in module, but specifically these two things, if they existed in module, they're going to be overwritten. If they didn't exist, they're going to be added. I think that's yeah. If you haven't seen object-oriented programming before, then don't worry, we won't use it too much in this book. It's object-oriented syntax. Note that the input of the model is a tensor of shape batch size times 2, where the first column X contains the user IDs and the second column contains the movie IDs. As explained before, we used embedding layers to represent our matrices of users and the movie latent factors. So what was the times 2? So one is the IDs and one is the user IDs, one is the movie IDs.
Yeah.
Yeah. Okay, that's the size. That's the size 2. Now that we have defined our architecture and created our parameter matrices, we need to create a learner to optimize our model. In the past, we have used special functions such as CNN learner, which set up everything for us for a particular application. Since we're doing this from scratch here, we'll use the plain learner class. Oh, I guess I missed something. This is what I missed. So wait, I kind of skipped that, huh? Inheritance, PyTorch already provides, can add additional behavior to an existing class. PyTorch already provides a module class, which provides some basic foundations that we want to build on. So add the name of this superclass after the name of the class that we're defining, as shown in the following example. So that's just this. The final thing that you need to know to create a new PyTorch module is why do we want to create a module? I kind of got like spaced out on that.
It seems like we just want to like build on top of whatever module has. So still have like the functions that were defined in module, but now we're defining this new dot product class.
What is a module though?
I don't know, something in PyTorch. So
what are we trying to do with this? It's just some dot product.
I think you're just, it's just an introduction into like creating new classes that are leveraging some of these other classes in PyTorch. And it's also like weird that this is getting introduced now, but
why is that?
I don't know. It feels like you should, I don't know. Maybe it's because we keep going on these tangents that do involve a good amount of Python knowledge, at least. Yeah.
But it's fun, you don't really need to know anything about it.
That's
but
what,
it's kind of nice when it's nice when it gets introduced, when you actually need to know a little bit about it. I don't know why you need to know about it now. Actually, that's true. You could just continue using this syntax without really knowing anything about it.
It even says like you're not going to be doing anything with this.
So in terms of the baseball, you're trying to say the baseball game is introducing some rules at the point when we don't actually want to hear about them or something.
No, if to use the baseball
it's a pep
example,
talk.
if fast.ai is the game of baseball, then this is like, okay, well, we learned how to play baseball and everything. Now you guys are gonna go just take a tour of the factory of where they make the bats or where they make the balls, and you guys can watch people stitch them together. And you're not doing anything because we're creating the class for you, but we'll give you a souvenir on your way out. I hope you enjoyed this little tour.
Cool.
That's what it kind of feels like, no?
I'd be interested in that baseball ball factory tour.
Well, when all the travel restrictions are lifted and everything, and you want to come to the U.S., we'll go to a museum.
Go to Cooperstown.
There you go.
Where is that?
It's in New York State somewhere.
There you go. Well, we come
They make
down to
baseballs?
New York, and we'll go there.
Oh, you'd have to go to the Rawlings factory for the baseball.
Rawlings.
Another tangent.
Or I was thinking of going. down
No,
to,
it's
like, Louisville.
It's RAW down. Yeah.
Rawlings.
Yeah.
Like that?
Yep.
Yeah.
I was thinking of going to like the Louisville.
Oh yeah, that would be the
baseball
baseball bat. Yeah. Yeah, Rawlings is more baseballs.
Where is it? Oh, it's in Missouri.
That doesn't look like a baseball. I mean, I'm
Well, they make a
no
bunch of
American,
sports
but
You can learn about all of these American sports, Martin.
okay. Rawlings. So that's a thing, huh?
Yep.
Whoa. Oh, sorry. 1887. That's pretty old, considering George and Alfred Rawlings. Okay. Sorry. I'm way too. Someone else should read. Who wants to read?
And I gotta go in like 10 minutes.
So you should just do a
guys
paragraph, a quick paragraph, right?
Wait, you went robotic on me there. I don't know what you said.
You should do a quick paragraph.
Okay. The first thing we can do to make this model a little bit better is to force those predictions to be between 0 and 5. For this, we just use sigmoid range like in brackets. One thing we discovered empirically is that it's better to have the range go a little bit over 5. So we use 0, 5.5. So basically they just add that last argument and then the last line there. Mm-hmm. And then also the return function.
So this is just because the range or the factors, we decided that we wanted 5 factors, right?
No, so the ratings go from 0 to 5.
Oh, the 0 to 5, okay.
Mm-hmm.
So they go 5.5 because like the sigmoid function never actually reaches 5 because it's like an asymptote there. So they go a little bit above.
Got it.
I guess that helps.
Sounds.
I wonder how you choose what's the right a little bit above. So I don't know why I speak at all. Okay, train. More. You can do one more.
This is a reasonable start, but we can do better. One obvious missing piece is that some users are just more positive or negative in their recommendations than others. And some movies are just plain better or worse than others. But in our dot product representation, we do not have any way to encode either of these things. If all you can say about a movie is, for instance, that it is very sci-fi, very action-oriented, and not very old, then you don't really have any way to say whether most people like it. That's because at this point, we are just using weights. We do not have biases. If we have a single number for each user that we can add to our scores and ditto for each movie, that will handle this missing piece very nicely. So first of all, let's adjust our model architecture.
Mm-hmm. So this is going to be like a little salt of like this user is very critical or this movie is actually very good.
Yeah.
We
so it's basically like if you look at a graph on like a 2D, so like y equals mx plus b. Are you guys familiar with that? So m is the slope So B would be this bias, just like moving that graph. So if it's y equals x, you would have y equals x plus 2 or whatever. So it doesn't go through the origin.
Gotcha. So we did some training here.
Okay, so 0.88.
And so now we're saying, okay, so this is going to get better probably. What was our first result?
1.
Getting 0.88. 0.88.
Okay. So let's train
And
this
then we
again.
do some more training.
Reading a little.
Instead of being better, it ends up being worse. At least at the end of training. Why is that? If we look at both trainings carefully, we can see that the validation loss stopped improving in the middle and started to get worse. As we've seen, this is a clear indication of overfitting. In this case, there's no way to use data augmentation, so we will have to use another regularization technique. One approach that can be helpful is weight decay.
Oh, interesting.
Yeah. Wow.
Okay, so that's a the first one is 95 and then it goes down. Yeah, it's interesting that you get that images have this advantage that you can do these stretchings and croppings and stuff to them, and you can't really do that with tabular data. That makes sense.
All right.
So yeah, so basically in that last model, it just learned the training data like way too well, because as you can see, the training loss went super low while the validation actually like went up. So that's clear indication of overfitting.
Oh, interesting. Okay, so you're saying when this goes really low, when the loss goes really low.
So so like if you just looked at the training loss, you'd say like, oh, this is doing so much better, right? But then when you also look at the validation loss,
I see.
After the third epoch, or I guess that's the fourth epoch, I don't know, the validation actually goes up. So it's actually getting worse.
Okay, I see. Interesting.
So like if you were to run more epochs, the training loss would probably get better, but the validation loss
would keep increasing too.
Probably.
So this is this step is the interesting one in that case. So far, this makes sense. We have a high loss in the validation. It keeps going down with training, but then here, this keeps going down. This goes up, and that's like okay, nice, cool. That's a good thing to keep in mind. Oh, what were the previous ones? Everything wrong.
They were all going. No, I guess that last one.
No, that's not everything wrong, but we don't know exactly what. That's just like a loss in terms of just like a number value.
Okay, it's not
like 100% wrong.
Okay.
Right?
Okay, but it's similar. It keeps going up here then.
Yeah. So at the end it goes up a bit.
Yeah. Interesting. All right, cool. So now we're gonna learn about weight decay.
Are we gonna do that?
How?
This is where we are. Yeah, I guess.
How much?
We're not very far through this lesson at all.
This lesson took me a while.
I mean, so it ends up being 3 streams. It's all good.
So whatever, right? Weight decay. Okay, I see. Yeah, I guess we can do some more here.
Yeah.
Maybe another half an hour or something. Sounds good.
I'm good with that.
Cool. Whoa, you just motivated me. Look at that nice image. Okay, cool. Nicholas?
Sure. All right, weight decay, or L2 regularization, consists in adding to your loss function the sum of all the weights squared. Why do that? Because when we compute the gradients, it will add a contribution to them that will encourage the weights to be as small as possible. Why Why would it prevent overfitting? The idea is that the larger the coefficients are, the sharper canyons we will have in the loss function. If we take the basic example of a parabola, y equals a plus x squared, the larger a is more narrow. The larger a is, the more narrow the parabola is. Okay.
Pretty. We're just going to see the same thing. I don't know why I ran it.
Yeah.
So letting your model learn high parameters might cause it to fit all the data points in the training set with an over complex function that has very sharp changes, which will lead to overfitting. Limiting your weights from growing too much is going to hinder the training of the model, but it will yield a state where it generalizes better. Going back to the theory briefly, weight decay, or just WD, is a parameter that controls the sum of squares we add to our loss, assuming parameters is a tensor of all parameters. Okay, so loss with WD is equal loss plus WD times parameters squared and the sum of that. Got it, okay.
I think I just zoned out.
So those weights would be like in the movie factors, like I believe that those would be the weights. So it's trying to, I could be totally wrong. But yeah, like it's trying to minimize how high, like how large those values get, unless it like absolutely needs it to, because the higher the value those values are, it adds to the loss. So you get a bigger loss if your parameter values are larger.
Okay.
So I like what it turns out to be is like it just softens. Like if this was just like a 2D graph, like if you had like before weight decay and the line was super like noisy and like had a lot of noise in it, I guess. I don't know how else to say that. It would just soften. It would just make it more smooth.
Cool.
And these are the random numbers that we chose in the beginning, right?
Which ones?
So like you're saying,
yeah,
like
that's
the
what I
numbers.
believe. So yeah.
Okay. Cool. So
I could be wrong, but that's my understanding. Yeah.
But that's why if you go back to the graph, this pretty one, right? You want it closer to that one, or you want the smaller numbers because it's got more room to kind of breathe, right?
Yeah.
Cool.
Sounds good.
Cool. All right. In practice, though, it would be very inefficient and maybe numerically unstable to compute that big sum and add it to the loss. If you remember a little bit of high school math, you might recall that the derivative of p squared with respect to p is 2p. So adding that big sum to our loss is exactly the same as doing parameters dot gradient plus equals the weights times 2 times the parameters.
Weight decay times 2 times parameters.
Yeah. Weight decay times 2 times parameters. And that is, okay. So we're just incrementing the gradient.
Yeah, something like that.
So in practice, since WD is a parameter that we choose, we can just make it twice as big. So we don't even need the squared in this equation. To use weight decay in fast.ai, just pass WD in your call to fit or fit one cycle. Got it. So you want to run that, Martin? So the dot product bias, okay, moves 50.
Did Martin's exercise ball deflate?
I think so.
It's changing position.
Okay, I have to go. I got a job interview in 20 minutes, so.
Oh.
Best of luck.
Yeah, thank you. Thanks for having me on. I don't know if I was a valuable addition or not.
You were definitely a valuable addition.
Definitely.
Sure. Yeah.
Thanks for joining.
Yeah, thanks for joining us.
Yeah, if you guys want me back on, if not, that's fine. But yeah, I'll totally understand.
No, totally feel free to join if you want.
Yeah.
Like we're just gonna be on that same like we have a couple of maybe stream time changes that we still have to figure out for next week, because Nick's maybe also gonna have a job next week, and I got a couple of other things for my job I have to do.
Okay,
so
sweet.
It might be a little, I don't know exactly. It's probably gonna shake up a little in the coming time, but I don't know. But you're always welcome to join.
Yep.
Okay, sounds good. Okay, I'll talk to you guys later. Enjoy the last
20 minutes
bit of the stream. Hopefully it goes smoothly.
All right. Thanks for joining.
I'll see you guys later.
Good luck for your job interview.
Yes, best of luck in the interview.
Yeah, thank you. How do I end this?
I think you can
there it is.
Yeah.
All right.
Bye.
Take care. That was so nice.
Yeah, totally. He's gone. Poof.
All right. Now it's back to just our shenanigans.
Yeah, I was zoning out towards the end now, and I hope that you two would just continue. But now I have to put my brain back into it, huh? Or you just handle that.
Much better.
What?
I'm just reading.
Much better. Much better.
Much better.
Oh wait, but so I like that thing of like comparing these two. If this goes down and this starts going up again, that's like a kind of nice, thing to look out for.
Yeah.
So it's still going up a bit here, but not a ton.
Yeah.
Between those two.
The 1000th.
Yeah.
So.
Much better.
Much better, yeah. Okay, so we got another 15-20 minutes, I would say.
Yeah, let me see. I think this makes sense. We go through this last part and then stop by interpreting by the next big heading. Yeah. Cool.
Okay, so creating our own embedding module. So far we've used embedding without thinking about how it really works. Well, we tried to think about how it works.
Yeah.
Maybe we shouldn't have. All right. Let's recreate .product bias without using this class. We'll need a randomly initialized weight matrix for each of the embeddings. We have to be careful, however. Recall from open close bracket that optimizers require that they get all the parameters from a module from the module's parameters method. Okay. However, this does not happen fully automatically. We just add a tensor as an attribute to a module. It will not be included. If we just add a tensor as an attribute to a module, it will not be included in parameters. Okay. So now we are.
So what? How do you have to add it? Okay.
It will not be included in parameters. If we just add a tensor as an attribute to a module, so this isn't.
Wait. So what is it doing there? So we make a new class, just calling it T, inheriting from module, initialize with an additional tensor, I guess, just filled with ones. And now we're checking, okay, it's not part of the parameters. That's just a test.
What is this L? Just list?
Yeah. Perhaps a list of items, but can also index with lists.
Okay, so this is saying that T has no parameters, or doesn't.
Even though we added one in the initialization, it's not part of parameters, yeah.
So to tell module that we want to treat a tensor as a parameter, we have to wrap it in the NN parameter class. This class doesn't actually add any functionality other than automatically calling requires grad for us. It's only used as a marker to show what to include in parameters. So class T, so this is the same thing, but we're passing in. Can you say
we're doing this
self.a is equal to parameters, NN parameter torch. Okay.
Yeah,
so what is NN was what? Is that?
I think it's neural networks. Does that make sense?
And that
no,
comes
probably
in
not.
From fast.ai.
Let's see. It's double question mark it NN question mark
All
question
PyTorch
mark.
modules use NN parameter. Okay. So
it's a module torch.neural net. I think it's torch neural networks.
Yeah. Okay.
PyTorch.
Okay, so all PyTorch modules use NN.parameter for any trainable parameters, which is why we haven't needed to explicitly use this wrapper up until now. Okay.
Yeah, like all of this NN.linear, they do it by default.
Okay.
Is what this is saying. Yeah.
All right. t.8, yep, is a parameter.
Yeah, it's this NN. Yeah.
We can create a tensor as a parameter with random initialization like so. So create params, return NN parameter, and then just, okay, torch.0 size dot normal.
So it's just making a normal distribution. Like I think it initializes an empty array matrix, an empty tensor filled with zeros of a certain size that you pass in, and then fills this up with a normal distribution of values.
What is that asterisk size? What does that mean?
It's just like generally these are just arguments. Like it's a list of arguments. I'm not sure what exactly it means in here, but generally if you pass something like that to a Python, the definition of a Python function. Oh wait, so this is an actual. It must be unpacking it or something. I don't know. Let's see.
That's what the asterisk does in Python is unpack a list.
Well, there's two things. Like if you do something like that, and you say args, right? So if you do it in the definition, then you can say.
Right. Yeah. I'm familiar with this.
You know this? Okay. Yeah.
So you could pass infinitely amount of arguments in that.
Correct.
Right?
Yeah, I could say.
If you remove that from the definition, right, like how it's saying size, is it the same thing, or is it kind of, it's like reverse unpacking it, right? Saying like,
I wonder. Yeah, I don't know. Let's see. So, okay, we ran this already. Let's do something else in there. Let me just remake that. See what it does if we do this.
Because I wonder if this is like, in some languages you have this like triple dot syntax that like unpacks. Must be iterable.
Argument after star must be an iterable, not an integer.
Okay.
So maybe it does something like, so I can put an iterable in there, like a list, and then see what it does.
So so it prints each one, not as a list, but it unpacks it, right?
Maybe.
Like if you printed just that list. Maybe put a space between all of them. Yep.
Yeah, so it prints each item of the iterable separately. That's what it does. Interesting. Okay. I wonder what this is called. I don't know.
So it just iterates over that. So that's kind of like a nice little nice little trick to kind of replace a for loop if you needed to get everything. Do something with each one. So torch that zeros for all of the I wonder why it's called size. Let's see how we use it.
Size is just the input. Yeah, okay. Let's see. Let's use this to create dot product bias again, but without embedding.
So what was the function name?
The function name was create params.
Create params, okay.
Params.
And then if we go down.
And we're using it where?
Oh, right there on all of this.
There it is.
Yeah. Okay. So in that case, that's interesting because n_users and n factors are also tensors. So this, you're passing in a matrix now. So it's going to return back probably the same size of the matrix as well. So like size, 2 by however many in n users and n factors. So it'll persist that.
Interesting. Wait, so you're saying this is going to make one parameter that is a matrix that is like of size of users times factors?
I think it's going to create a matrix of 2 rows with n users and then n factors like length. So like column, if it's you think of it as like n users, let's say, is length of 50 and n factors is length of 50. I think it's just going to have a 2 by 50 matrix.
Okay.
And that asterisk is just expanding, maybe like, I don't know if it's what it's doing under the hood, like recursively or something, but that seems what it's like, iterating kind of and maintaining the size and shape.
Okay.
My theory. Who knows?
Then let's train it again to check we get around the same results we saw in the previous section. Now let's take a look what our model has learned. Not today. Wonder what this is called. Star unpacking Python. Oh, this sounds okay. Okay, so I guess the star makes normal unpacking irrelevant of the size of the input thing. So if you would do, right, like if I make a function that returns two things, like 2, 3 or whatever, like it returns 2 values, then I could like run it and assign to A, B, fun, like that. And that it unpacks, but like that's an unpacking. But if I would do like that works, so I mean, so if I say A is now 2 and B is 3.
Sure.
But if I would do A, B, C, then it wouldn't work because the unpacking doesn't work. So if I do something, I don't know how I can translate that now. Let's do, I guess, this size.
Yeah, and then return asterisk size.
Asterisk size, and then this would work if I pass in 3 things.
Right.
Like if I say 1, 2, 3, this would work, and it would work. This no, it doesn't. Fun takes. Because I didn't run this. Sorry. Interesting. Yeah, I'm not familiar with this. Can't do a start expression here. Where can I use it? I can use it to a print call.
Maybe not in, maybe not in
that worked before. But then it's not actually unpacking. So it's not unpacking in an assignment, it's just unpacking within there. I don't know. Anyways.
It seems like, maybe you can't return.
So I mean, that's the type of unpacking that I know, right? You can also do this with a simpler case. I could have a tuple here and I can say 1, 2, 3.
Yeah.
That's just tuple unpacking and it puts it there. And then we have these assigned. But must know the length of the sequence you're unpacking in advance. Okay. If you wanted to find the largest, second largest, we'll get an exception. Too many values to unpack. I often rely on indexing and slicing. For example, when I want to extract the largest, second largest from a list, that's how we can do it. Okay. Still doesn't have anything to do with the star.
It seems like you just can't include it as the only thing in the return statement.
Here's something.
Like you need to maybe this is my also misunderstanding of what Python return stuff, but that's what it sounds like. So the start syntax allows one part of the unpacking assignment to receive all values that do not match any other part of the unpacking pattern.
So I could use it like that. I could just say, this is a dumb code, but whatever. And then I can say ABC is so now I pass in
You pass in
a list 1, 2, 3, 4, 5, 6. And then if I say this D, then 1, let's make it a bit more easier to keep track of. So A and B, A should go to 1.
And then 3, 4, 5, 6 is going to be a list.
3, 4, 5, 6 should be a list that's assigned to C.
Okay.
Oops. Didn't run that. So print A, print B, print C.
Cool.
Okay. Interesting. Okay, and so why is this used in here? So it just catches anything that, because
I just think it's like you're passing in this, you're unpacking the size or like the dimensions. That's what I think. Or you're just making zeros out of everything.
But the way that we're using it here, right? Like, so we're passing one list with 2 values in there. So it's just gonna pass this thing in there. Am I misunderstanding that?
No.
It's just gonna take this list and pass it in here.
Correct. It's gonna pass. I think it's gonna unpack and pass.
I don't think it does. I mean, I'm not sure.
Point, yeah. What is torch.zeros? How does that? I imagine it's just.
I think it just makes I think it just makes a tensor of zeros.
So that takes in
zero size, star. Oh, none.
Returns a tensor filled with the scalar value 0 with the shape defined by the variable size. Yeah, that's a good question. I don't know why, if they're doing the star in zeros, why they're doing the star in this create params as well.
Well, it looks like it requires that as the input, like a start one. But this is very unfamiliar for me also to read something like that.
But didn't you like a starred one? Because that could just say like star args, right? And then we go back to the function that you defined before, where it's just like anything, we don't really care what you pass in. We're just going to take whatever you passed in, that, those dimensions, and return back a matrix of zeros.
But I did mention that then you would pass then you would pass them not in a list, like not in one item, but it would actually, if it can take as many arguments as you want, you could just say number users, number factors, and if we want to make it bigger, 4200 or whatever. And it would be fine because we have the star, so it would just take whatever arguments come in there.
I see what you mean. Yeah, but then in this create params, I guess, I don't know.
Okay. Mystery. This mystery shall remain unsolved. Until next time.
All right, so let's run that last. I think we're just about running.
I think we're done. We already ran it.
Oh, we did? Okay.
Yeah. This is our output.
So in this case, it actually does keep going down every time.
Oh, wow. Yeah. That's nice.
Nice. Now let's take a look at what our model learned.
Nope. Not today.
All right, cool. So this was fun.
Okay, interpreting embeddings and biases, bootstrapping, deep learning, conclusion, questionnaire. Okay, we got a bunch of stuff set up for next time.
It seems like we could
maybe
do it in 2 streams. Cool. This was fun. Very informative.
Yeah, interesting to have someone else on.
Mm-hmm.
Like interesting dynamics, also with like 3 people instead of 2 people and everything.
Yeah. Yeah, it was nice. I think he moved us along, and we had fewer tangents for sure.
Possibly.
Yeah. So, but no, this was cool. So Monday. Yeah. So I guess we have to figure out a schedule that most likely Monday will be unaffected, it seems, but next Thursday may be affected.
Yeah, I don't think next Thursday might not happen or something else, but I think Monday should still be as is.
Yeah. All right. So we'll probably also know around Monday if Thursday's happening. Or what time? I'm so tired.
Well, good luck to your job interview as well.
Yes, thank you. That is also a little bit later. I've got 3 hours.
Bit of time.
Yes.
Chillax.
All right. Well, see everybody on Monday.
All right. Bye-bye.
Bye, everybody.